very exciting to actually be here. What we're going to do today, as Dad sort of began to introduce, is we're going to have a conversation that will hopefully stimulate you guys to think like Dad thinks, think differently about construction. In order to look at his family of technologies, each of which, I call them a family because each of them sort of is a byproduct of the thing that preceded it. And it's not so much an evolution of a technology, but rather a conversation or a back and forth looking at different aspects critically and then coming up with solutions that turn out to be whole new ideas. Isn't it nice to be a genius? And what we're going to do is we're going to start looking a little bit at history. Then we're going to look at a very artificial, superficial level at how ideas and how progress works. Then we're going to use my dad's technologies and the family of systems to sort of illustrate some of those ideas. Then we're going to look at the now and perhaps then look into the future. In terms of history, I thought it'd be relevant to start in a time when a lot was happening in technology, a time when things were really changing and technology was driving it. So across a variety of different industries, things were happening. In the communication industry, they just invented the telegraph. Now, this seems archaic to us, but that thing was so scary that the first Morse code message that was sent, as many of you know, was, "What hath God wrought?" Sort of illustrating like this thing is just seriously badass and we're scared of what we've created. Similarly, in transportation, you know, the locomotive was an incredibly technological sort of advancement. And I like to illustrate that by referencing William Turner's works, Wind, Rain, and Speed, I think it was. It was like the cutting edge. And also seriously badass, my favorite, the Crystal Palace. As you all know, Joseph Paxton, a gardener, self-taught, invented literally a completely new way of building, a way that was modular and based on the size of pane glass that he could get at the time, and that had a new structural system that was based on steel frame construction, and along with it had a whole new, very, very modern aesthetic. And it was, you know, it sort of made the idea of prefabrication real. This thing, 93,000 square meters, 5 stories tall, was designed and built and conceived in 8 months. I mean, ridiculously advanced, right? So 1850s, thumbs up in terms of technology. Now, since then, a lot of things has happened too. In fact, you could say that the growth in communication has been, you know, absolutely logarithmic. And today we have, you know, all of human knowledge at our fingertips with Google and supercomputers that are really phones, or are they supercomputers? Anyway, they're pocket size. And then Facebook and all these other technologies that make communication just a completely new thing. Similarly, in transportation, we have supersonic jet planes that can cause all sorts of havoc. We have green cars at a high performance. We even have a rover cruising around the surface of Mars. So quite extraordinary things have happened in a variety of different directions within transportation. But not so good on the construction front. We're really building the exact same way as William Paxton had developed 150 years ago. So why is that? I mean, after all, in your opinion, when you look at this, which is the bigger industry? Which is the one that is the bigger percentage of the world's GDP? Ours, essentially. Which has the most environmental impact? Which is the biggest polluter by far? almost doubling the impact of the next runner-up. This one, which employs more people, and very importantly, which is represents a basic human need, one of the 3 basic human needs, construction. So how can we account for this? So let's look a little bit at how ideas and how progress works. If you use technology, if you imagine that Joseph Paxton was down here, right, at the beginning of this new technology, then I'm just going to walk in here. So here's Joseph. Then you have Gustav Eiffel doing towers and other buildings. Then you have these different applications like train stations, bridges, the bridge of 4th or 5th or 5th or 4th, whatever it is. And that's where the growth curve begins, you know, this sort of logarithmic growth curve that we like. But then it never really goes any steeper than that. But still things are happening. The modernist movement comes and develops a new aesthetic around steel frames. Eventually, however, it tapers off. And that one technology can only go so far. That's what's happened here. In the other instances, you have other ideas coming along. We're just not happy only with Joseph Paxton's idea, but new ideas come along, and they develop and take over the original idea as disruptive technologies. When you have a series of these things taking each other over, you get that, what we call in America, a hockey stick kind of growth curve, that logarithmic growth curve, which is evolution, which we like. And that's what you have in these other 2 industries. So, you know, we need to do this sort of thing. We need to think this way. We need to think a little bit like my father. He has ideas, you know. He has ideas about how you build. And one particular day, he was playing tennis with a buddy of his. And did you win or lose?
I think that I lost.
Well, you may have lost the game. But there were other advantages. He was playing under one of those balloons, and it was snowing. And he didn't really perceive that it was snowing because there wasn't really a big pressure differential without snow and with snow. But a lot of snow had fallen, so much that essentially the 2 of them were trapped inside. So he started thinking about, my God, you know, I'm playing tennis here, and all of that snow load is up on top of this roof, obviously with very little pressure. Out of that came this new way of building, that not only suggests to the seemingly crazy notion of pouring concrete on the ground and inflating it as if it was a soap bubble, but actually he pulls it off. I'm going to show you more or less how this works in diagram form. Then we're going to cut to a quick movie that shows the same thing, but it's, you know, real life. And then we'll come back to the slideshow. So the way it works is this. You begin with a slab-on-grade foundation. It's round, and the perimeter is thickened with what we call a ring beam. And there's a pump at the end of a tube that starts in the middle of the slab-on-grade. Onto the slab-on-grade, he fixes a membrane. So the membrane is secured around the perimeter of this foundation. Then he stretches springs from one side of the foundation to the other, creating a pattern that's like this sort of mesh of springs. And then he slides rebar into the spring. So if I'm standing on one side of the foundation, I slide from this side, and there's somebody over there who's sliding steel in from this side, and there's an overlap in the middle. Eventually he'll inflate it, and there'll still be enough overlap for the rebar to be continuous from a structural standpoint. Again, interrupt me if there's questions or whatever. Now, at the 2D level, he then pours concrete on top of the springs and puts a second membrane on top of the concrete. Then he applies air pressure. Interestingly, around 0.5 psi, 12 inches, sorry, that's all American, but very, very little air pressure, about the same amount of air pressure as you use when you smoke a cigarette, if you smoke a cigarette, which I hope none of you do, but I assume all of you do, because we are in England. So very low air pressure, and this entire mass of concrete, we're talking about 350 reinforced concrete. I always make that mistake. All of that comes up, and it's 350 metric tons.
Yes.
So a ton of, 350 tons of weight comes up with this very low air pressure. Of course, that's because each square inch of that has less weight than half a pound. And that would be helpful if we knew what half a pound weighs, but I'm sure you all do. Now, there's a coil on top of the middle here, and it has these electrical cables that have these vibrators attached to them. And you get guys to sort of circle around the dome with these vibrators, and that vibrates the air bubbles out. And then you get a concrete shell, and the concrete shell dries, and you can cut the openings out. So again, I said I'd go to a movie.
How long does it have to be inflated for?
Depending on the size of the building. If the size is, say, 12 meters in diameter, like the first one that I built with this guy that was shocked about seeing this coming back from this event, it takes only 1 day. And indeed, I was really silly leaving the blower for the entire night by itself, because say that the electrical power was going off, we were in trouble. But I was lucky, the blower was working for the entire time, and so the first Binishell was up, and it's still there now.
So cut to this movie, and it's fabulous 1970s soundtrack. I'm actually going to speak over this because I don't know how to turn it down. Let's try this. There we are. I got it. Thank you. So essentially, this is the first membrane, and they were doing a test inflation right there at the beginning. And here is the steel that's come in and been stretched, and of course the rebar slipped inside the steel. And now they're pouring the concrete flat on top of the steel, and then we have then they're troweling the concrete flat, and then we have a second membrane that's folded over the entire wet concrete surface, and then you have magic. Now I can turn it up again because I know you all love 70s.
It is the only power which lifts the concrete into the desired shape and eliminates the tedious and expensive conventional methods which are also so time-consuming.
There's a time-lapse view showing this thing coming up in just a second.
The shell takes about an hour to rise to the position. The inflation is best illustrated by the use of our time-lapse camera.
So this is a 40-meter diameter dome coming up in an hour, shaped by air pressure in 1978 or something.
Once the shell is up, the vibrators are started
So then they vibrate it,
and surface above the render line.
finish the exterior, both from a waterproofing and insulation, thermal insulation standpoint. And then they cut openings and do the interior finishes.
You can see this movie on my website entirely, which is interesting. Now, we don't want to waste too much of your time, but if you want to see the details, you can see it.
So a number of other Binishells were built after the prototype. And it's interesting, if you guys are interested, I encourage you to ask my father. Otherwise, you can read about it in the book. But one of the next ones was actually, we went from this small town outside of Bologna to the University of Columbia campus in New York with an amazing mathematician called Mario Salvadori. It's a fun story. But another fun one is the fact that Dad designed this house for, if you are a film buff, you'll recognize the name Monica Vitti or Michelangelo Antonioni. He did the film Blow Up. She did a lot of other stuff too, and apparently was a very good cook. But this is on the Costa Smeralda in Sardinia, and it's a beautiful, beautiful dome that I encourage you also to ask Dad about the process of designing and contextualizing. He built these in Japan in 1970 for a World Expo. This one's in Australia. It's a public school library. You can see the really interesting sort of opening that he cut into the shell. And also, you can see how thin the shell is. They're about 2.5 inches thick. Of course, a dome is the most efficient structural system you can design in. So you can leverage that efficiency to use less material in a more effective and environmental way. Secondly, monolithic domes are thermal bridge free, and that has a huge impact on their environmental advantages. We'll get back to that later. This is a 64,000 square foot, about 6,300 square meters. Series of shelves. This is actually the one that you saw in the movie. Each one of these is 40 meters in diameter, and the entire complex was built in around 8 months. Not quite Joseph Paxton, but you know, we're trying. This is a system called the Binishell system that I've rebranded Binishell System 4 with some modifications. It resulted, and here's where I begin to sort of try to illustrate how, you know, one system led to the next. It resulted from a lecture just like this. Dad was speaking, and one of the students sort of put his hand up and said, you know, this is all fine and good, but you know, I don't like circular buildings, and you know, my bed's square and my table's rectangular and all this other stuff. It just doesn't fit my lifestyle. Can't you do a square one? And while you're at it, I think that, you know, you're being very silly, wasting all that stuff that you're cutting away to make your openings. Why don't you just have the openings sort of appear magically and do away with the ring beam that you have to reinforce the opening with? And literally, this is some guy's question, apparently. I wasn't there. But Dad actually came back 1 year later with this solution where, as you can see, this square-based dome that has the corners cut away has these, what he called spinnakers in the corners. And as it rises, these spinnakers balloon out. And there's a number of advantages here. First of all, clearly not pouring in the middle, in the corners here, it gets you the openings in the end. That's one advantage. No waste. Secondly, the 4 spinnakers stabilize the inflation process. So that helps. But really interestingly is, and I think this illustrates what happens when you work with nature versus working away from nature or against nature, which is what the construction industry typically does. When you work with nature, it works for you. And so what happens is that there's a differential curvature that exists, or radius of curvature, of course, that exists between the central portion of the dome and the spinnakers. And what that results in is a beautiful stiffening perimeter for the opening that also is a little natural gutter. So it works in so many different ways because nature's like that. So you know, brilliant efficiency from a design and structural standpoint. From there, he challenged himself to build bigger. And the constraints there were the weight of the membrane. These are actually pretty, you know, substantial membranes. I forgot to mention that you can reuse the membranes. So they're made of a substantial material, which is the same material that you see in those stadia that have sort of fabric tensile roofs. So it gets really heavy as you get bigger, especially. And so what he did is he, instead of having one big piece, he had a series of rolls that, like a Union Jack, kind of, you know, fold over each other and create an airproof membrane. And the cool thing about that is obviously rolls are a lot easier to fabricate, a lot cheaper. You can roll them back up and reuse them. A lot of cool things that come out of that. So that was one constraint that he wanted to address. And then the other one was that as the dome got bigger, you know, you were limited by the concrete, because on one side of the dome it would start setting as you're still pouring the other side. So he minimized the use of concrete by introducing these triangular panels. So essentially what you get is a you know, geodesic dome where the tensile elements are in concrete, and then you have the panels that are infill elements that you can either keep in or keep out, or insulate acoustically. It allows all sorts of different variation. So this is the Bini system. I call it Binishell system 2. Then you have this one where he said, well, you know, why do we need concrete at all? So the way that this system works is that you have these nodes that connect a series of members that are able to rotate up and down and also torsionally. And the members can expand telescopically and sort of click into place in the same way that, you know, an umbrella does. So as you inflate the membrane, which eventually then is hung onto the steel, at first it guides the steel up until these pieces of steel lock into place, and you get this structure. Now, the advantage of this structure, of course, is that A, you don't need concrete, so you can build it really big. But B, you don't use concrete, so you can demount it. You can take, it's a kit that you can take away. And in fact, that's why they used it as sort of press facilities for the Italian World Cup in 1990.
Membrane that you would be using to
Inflate it.
concrete.
Same material, yeah.
You see, this material can change, can have some different ability to be flexible or not if the change in temperature is dramatic. So initially, because of this reason, I use neoprene reinforced by nylon. And if you have a very low temperature, for example, in Canada, we have been using this because of the temperature. And this is PVC reinforced with polyester. It is a standard thing. And this is temperature affected by. No? So depend where you are building the structure, you change the membrane.
So this system was used for a number of different applications. Here's a World Fair application in Seville, military purposes, as hangars. And then from that system, you can see how, you know, a guy like him would arrive at this. Here is a mile-high city, or the infrastructure for a mile-high city. And the city itself is a series of skyscrapers that is hung within this sort of space frame pyramid. And the same sort of thinking was used to propose a way to build this thing. So this is a design that a company in Japan, one of the big construction companies called Shimizu, came up with, and they turned to Dad to sort of figure out how to build it. And he did, in theory. And if you're interested in this, there's a Discovery Channel show called Extreme Engineering. and it's really fun. So anyway, that's a series of technologies, and there's other ones. But now let's look a little bit at where we are today. Plato said that necessity is the mother of invention. And today, buildings are by far the biggest polluter, horribly so. They use 50% of our natural resources, which is really scary. 40% of our energy, which compares to around 23% for transportation. 40% of our carbon emissions come from buildings, and 35% of our solid waste stream. So clearly, lots to be proud about as aspiring architects. Did all of you know this? Huh?
I told them last year, but they've forgotten.
No, I didn't know it either, and I discovered it. This is what actually sort of changed my architectural path. And it's little known, but we have to recognize it. Do your research. These are the numbers. National Energy Education Development Project this year. From a safety perspective, we see this all the time, okay? What we're doing to the Earth is creating an ever more frequent series of natural disasters. The number of natural disasters actually doubles roughly every 10 years, okay? So that's bad enough. But the second part of that is that they're getting stronger, okay? So that's really bad, considering that the way we build with 90-degree angles is the least structurally effective way to build. It's the least structurally effective way to transfer loads. It's preposterously stupid. And yet, we are very happy in putting our lives at risk and our children's lives at risk in unsafe buildings. And the really extraordinary thing is that places like, Hurricane Alley in Florida, where, storms come every year, they're perfectly happy to, have the things sort of disappear in a cloud of rubbish and then rebuild the same thing.
The same way.
The same way, right?
Using
So it's absolutely crazy. It's absolutely nuts, okay? So we have to, the system is broken, and all you guys have to fix it, okay? So, woo, woo, woo. Other thing that's important is that 1 out of 4 people in the world is either homeless or living in substandard housing, okay? 1 out of 4 of us is homeless. Another horrible thing, we have to do something about the cost of construction. It's too expensive. It's too expensive to meet the demand and the need that's out there. So let's look a little bit at the future now. What we've done, what I sort of started doing with a friend of mine who was an engineer, who's a hell of a lot smarter than me, I said, look, I just had 2 girls, and I don't want to be part of the problem anymore. I need to be at least try to be part of the solution. And we started looking at this thing just sort of as a hobby, and we circled around and realized that my father's systems with some modifications could really begin to address these problems. And a lot of the modifications had already been done by smarter people who took materials and made them greener, made them more flexible, and did all that work for us. Another part of it was the codes. The codes had changed, and so we needed to bring Dad's systems up to code, and in so doing, modify them. And you know what? Why not simplify them and make them easier to build by unskilled labor that could be locally sourced? The other cool thing is that the only sector within construction which is growing logarithmically and is on course to take over regular construction is green construction. So there's a tremendous opportunity here to fill that need and to fill that opportunity. So we spoke to all these people who know things. We spoke to Clinton, we spoke to the president of UN Habitat, to the World Bank. It's very cool stuff. And then in the private sector, We also spoke to some of the big players like Lennar, one of the big home builders, and Primary Homes, just to sort of feel them out, see what they were interested in looking at. And out of that came a series of new systems, which we developed with Dad and some other people, all of which are smarter than me. And the first one was based on Dad's Binishell system. So I've sort of rebranded that Binishell system 4 because it's different now in the way it's built. So, but it still results in this incredibly economical but very, very environmental sort of shelter, which is about 900 square foot square-based dome with the openings built in. Then we looked at the parameters for low-cost housing as stipulated by some of these big organizations that I mentioned earlier. Out of that developed a double curvature vault, which is super cheap to build, super fast and super strong, and super green. So a whole new system to meet the needs of the developing world and of all the places that we need to build better in because they're being devastated by natural disasters. And then we also developed a new system which we call Binishell System 6, which results in these very sort of architecturally, I like to say, sexy designs. They're curvilinear, they're beautiful natural forms. And they're not natural in terms of sort of organic, where you force a material to be curved and therefore look like nature. But literally, these are designed by nature because it's Pascal's laws that create these shapes. And this gets back to the earlier point of when you use nature, it helps you. These are literally form-finding diagrams. These are as structurally effective as they can possibly be given this perimeter. So again, using nature helps. So what are the advantages? Well, there's a huge advantage with regards to reduced costs, and that's both from a sort of bottom line, dollars and cents, pounds and shillings, or environmental. Sorry? And from an environmental perspective. As you all know, the two biggest line items in construction are materials and labor. So when you use less of them, it becomes more affordable, both environmentally and from a cost perspective. And then if you use greener materials, of course, that helps as well. So big advantages. We're talking about 50% here and about 75% there. Right there, you have a game changer. Secondly, you use less energy over the lifespan of the building. Why? Because traditional buildings are built like we built cars in the 50s. They did everything but drive well. You know? They have all these wings and crazy design things that have nothing to do with what they actually do. And that's You're right. I used to drive a MGB GT67, and I just loved driving right next to one of these gigantic hulks and thinking, dude, what happened here? Because these are from the same year. Anyway, yes. Yeah, but Americans are very good at being wasteful. So they, let's just blame it on them for a second. They build actually stick frame buildings. And those are really bad because they're like bottles with holes in them from a heat perspective. They're literally everywhere there's holes for heat energy, which is the energy that buildings use most of, to escape. By just the nature of them, shells are monolithic, so they don't have thermal bridges. So once you eliminate thermal bridges, right there, you diminish energy use, according to the International Energy Agency, by about 79%. Extraordinary. So once you get rid of the thermal bridges, you just insulate it in the right way for that temperature zone, and you are doing a ton better than the Americans. Waste. 35% of the solid waste stream stems from construction. Why? Because building materials typically come in linear or sheet form and therefore are cut on site. They're also bundled. You get 10 for the price of 8. So you buy a couple more bundles, and if it turns out in the trash can, you win anyway from an economics perspective, which is all that counts, right? But when you use poured material, you actually only pour as much as you need. In the case of Binishells, you're using air as your formwork. So again, very, very little waste. And then another big thing is speed, construction speed. Why does that matter? Because if you're building disaster relief, the faster you provide these shelters for people, the more lives you're saving, which is a nice benefit. But the other thing is that the faster you build from a builder's perspective, the more projects you do and the more money you make. And that's important if you care about the environment, because if you make the people who end up building win, then they're more likely to choose your solution, which fits your criteria. So it's important to think about the market as well, I think. And then very importantly, when you build a structure that is shaped by air pressure, you build an inherently strong structure so that when a fire comes, it doesn't burn down because there's nothing to burn. When a high winds, typhoon or hurricane situation comes, again, it couldn't be more aerodynamic, so you're looking good there too. In terms of an earthquake, what you have is this sort of, low center of gravity, wide stance, distributing load situation versus, more like this, which is the typical situation. So you're doing as well as you can in earthquakes as well. And it goes from there, flooding and other sort of situations. Again, you can see this as sort of as some sort of marketing spin. But the point is, I think, that if you have an idea and it can help people, you also have to think about how to bring that idea efficiently to the market. And how do you do that? You make everybody win. You make the politicians win, you make the contractors win, but you also make the end user win. And you make him work by using local materials and local labor. So we're talking to some of the big contractors around the world, and they like it. They like what we're doing. It's a good thing for them, and it's a good thing for maybe everybody. We're very fortunate to have this sort of as a launch project. This is a house for an actor you all know and hopefully love in Malibu. And it's overlooking the Pacific Ocean. And it's just a great opportunity to sort of bring the idea out to the market. Here's an interior view of the same building. In terms of people who've looked at it and had positive things to say, Bill Clinton and his foreign policy advisor said that Binishells were the first system he'd ever seen that checked all the boxes for low-cost housing and disaster relief. The World Bank wrote us a really wonderful letter of endorsement, which is very difficult to come by, apparently. Forbes magazine named us one of the 31 names to know this year. And the U.S. Army Civil Corps of Engineers underwent 3 studies sort of attesting to the environmental, structural, and cost benefits of our systems. So what we're trying to do, and what we invite you guys also to try and do, is to be more like these other industries. Follow Dad's example, the new way of thinking, and bring construction into the 21st century. Thank you very much.
Well, at this point, I'd like to add a little thing. As I said to you, I don't like lectures in general, they are boring. And I like you to come to life and ask questions, because the future is on you. And I tell you that there is only an attitude that you have to establish in your brain. Try to think out of the box. And I wrote a book about this, and I hope you will have the opportunity to read it. At the present is in Italian, but will be translated soon in English. And I have to say that the input that the students that I was teaching to was tremendous in helping me in developing my technologies. The best example is the Binishell. You know, the guy at the end of the lesson room said, "Oh, I like your idea, but you made a lot of mistake in doing this." Yes, I like this attitude. I've made a lot of mistakes, and I think I'm going to do a lot of mistakes in the future, but it's the attitude of us to try to do something different, because we cannot afford not to do it in the future. Nick was describing very clearly something that is dangerous for all of us and for our kids. So I invite you really to think out of the box. But if you have any question, please do it. This should be a sort of discussion even. And
Could I start by just saying thank you very much, but could you, I know it's a question that was asked yesterday, but maybe you could describe your particular kind of favourite building, because there's a whole series of structures which are all created
Yes,
with using air, but is there a kind of...
Thank you, Will, for asking this question, because I learned a lot during the construction of this house in Sardinia. Is in Costa Paradiso, was made, and the guy that asked me to design his space of living, not a house. He says, "I want to live in the space, three-dimensional space. I hate flat floor. I like to live in a sculpture, naturally, inside a stone." Okay, so we were, you know, the first impact was a little bit embarrassing, because I didn't know what to answer to this question. And then he says, "Listen, I ask you to do something, to think about architectural design as I am thinking about it." I say, what do you think about architecture? I say, architecture, he says, is not only light, shade, but it is smell. Architecture is smell. Yes, it's smell. I want my house to smell, to have a flavor of the nature that is around it. He said, "Did you ever try to smell a piece of stone?" I said, "What?" He said, "Come with me, let's go in a quarry." And he forced a guy that was there to cut a big stone of granite. And as soon as this stone was cut, this guy, Michelangelo Antonio, put my nose there, said, "Try to smell it." And I tell you, the smell of the broken granite is incredible. It's fantastic. You see, I want you to give me a house with the smell of the stone. So I was requested to build a staircase with stone just cut. Not only that, he said, "You see, do you like juniper? This juniper?" "Yes, I want to smell juniper in my bedroom." So we cut slides of juniper, and we put the juniper on the ground. We smooth it, and in real term, when you walk inside this room, you feel this incredible smell. And said, smell the nature around you. And indeed, the dry herbs, rosemary, and so on, was so intense that he said, "My house must have the smell of the garden that is around you. So I built a garden in the middle of the house. Then he says, "The house must have also a sound." I never heard about this in my school of architecture in Florence. Yes, come here, listen the sound of the waves. You see, my house needs to have the sound of the waves inside. All right? And says, anything else? Yes, of course. The wind. I want to hear the wind that is coming from the sea. And this is the reason because I made a big opening here. So in real term, when you go in this house, in addition to the smell, you hear the sound of the environment around you. So I'm just telling you this, that when you have a client like this, try to follow, because you really learn a lot. I did learn a lot working for him. And I don't want to describe the other thing that he was teaching me about architecture of his house. So this is the house that thank you for asking the question, that I prefer, because it came out a lot of natural things that are part of it. Indeed, the surface here is made by rocks of pink, little pebbles of pink rocks. So this actually looks, this was in the beginning, but now we have all the trees going around, and it is part of the nature. Sometimes you don't see this structure, but when you walk inside, you are in an incredible environment, which is part of the environment that is outside. But also he said, I want you to build in space, not having a flat floor. So in this house, you live in different levels, and this gives you a totally different feeling. So this is the house that I like more between all my projects.
Aqua. Aqua.
Yes. Thank you.
Yep. Go ahead.
Say it again. I didn't understand.
Point out to us which parts of that house are shell technology or concrete
It's all shell technology.
Except for the openings.
Except the opening. I cut the opening after the shell was done. Is this? I didn't understand the question. This is a dome. It's a monolithic, elliptical shape dome, in which I cut the roof, so you can have rain and wind and sound inside. I cut the windows to see the sea when you walk inside. In this house, you walk in this house from the top, not from the bottom. So when you walk inside, you see the sea, because the entrance up there show this sea, and you see the movement of the sea from there, the light, the colors of the sea. So it is a house that is very much connected with nature, but it is one monolithic shell.
I think I've spotted another mistake.
Yeah, which one?
No, it's probably not right. But one of the things you said, which I think is one of the important things about technology, is the speed at which you can make them.
Yes.
So they are, as you said in the final thing, they're potentially very useful for an emergency situation or a disaster situation. You
Yeah.
can make them very quick.
Exactly.
As I understand it, at the moment, you need the ring beam to lock
Yes.
the small concrete dome. You need the ring beam to lock it together.
Small or big,
But
you need the ring beam.
Always, you need, like with
Yes.
a bridge shell, you
Yes.
can lock it. If we were in a disaster zone and we needed to make very quickly, as we may probably do in Syria right
Yes.
now for the winter, a lot of them, the most time involved is in digging into the ground to make a concrete bed on which to cast the domes. I think I'm right in saying more time taken on that than actually on.
Yes.
Is that right?
I think-
Partially right. The thing that I would like to mention, that during the disaster, you have all the infrastructure that is unusable. When you clean the infrastructure, you have the time to produce the footing system. Not only that, but in the traditional way, you pour concrete in a ring beam. But there are systems by which you can drill down anchoring points, and you can proceed.
That's what I was going to say.
This is the good.
Exactly.
Good.
Why
I,
build a-
I like the suggestion.
build a
I would like
continuous-
everybody give me some suggestion like this. Okay.
Sorry, I have a question.
Yes.
How do you use your system to build up?
You know, this is I tell you, this is a very interesting question, because it's the first question that I receive when I make lecture about Binishell. The first one was in Columbia University in New York. After, no, actually before the process of construction, I was requested by Associated Press to make a press release, press meeting. The first question was this. Now, I have, because of this, I started studying, since then, I'm talking about half a century ago, how to build up multi-story building. We are working on this. I've been working with a Japanese company called Shimizu, and we have obtained a solution by which, with a series of pressure and depressure, you can build a high-rise building. Using air, it is spectacular. The possibilities that you have, considering the use of air as energy, are infinite. I cannot talk about the details of this project because it is a patented thing. But soon you will hear a guy that was building up with pressure and depressure multi-story building. You were asking for.
We had a lecture here about 4 weeks ago about a man called Heinz Eisler.
I know him very well. Was a good friend of mine.
What do you think? I think
We are all, both of us.
his building technique seems to involve like very much like your technique, but without rebar.
No, come on. This is totally wrong.
Oh, really?
Totally wrong. He. Let me tell you, Hans Eisler is one of my masters. You know. He was a spectacular designer, a great artist, and he was able to build incredible monolithic thin shell structures. I'm talking many years ago. When the thin shell structures, geodesic domes, and tensile structure was, you know, the innovation of this period. I went to see him. I understood how he was building things, and I asked him, how much is the cost of the metal formwork or the wooden formwork in relation to the actual structure? And he says, well, maybe 5, 7, sometimes 12 times more. I said, what? Don't you think that this is nonsense? Like the guy, the student that told me that it was nonsense to build the dome and then cut portion of it? I said, what do you mean? This is the way we build. Why not using a different way to use a dynamic formwork? I don't know what you are talking about. Try and let me know. So he came to see my work in Italy. And I said, did you say that you were able to lift up with air a thin shell structure? I said, yes, look at that. And they built in front of his eyes a Binishell, and he could not believe it. And we were invited many times at the International Association for Shell Structures, and we were discussing. I was expressing my technology, my philosophy of construction. He was showing the beautiful, spectacular design that he was producing in Switzerland, maybe most of them. But he says, you know, Dante, at this time we were good friends, so your system could be long-lasting more than mine because the cost of air is pretty negligible. Could be polluted, but it's good to use it. So yes, but Isler is using road, steel bar, pouring concrete, spraying concrete, whatever, but he never used a process of dynamic lifting the entire structure as I did.
Can I paraphrase that? It's not what they built, it's how they built it. So in theory, you could build any one of Dante's,
Isler.
forms.
Most of them can be built, yes. Yes, absolutely. It's only a question to have, to devise the way to do it, like this one. You know, when you build a shell like this, and you build a ring beam with the same system, the opening, so you don't spend any time and you don't lose anything in relation with the process. The process is building. Like Nick was saying, if you work with nature helps you to do things in the best possible way.
So that is astonishing because all the Isla built, many of the Isla shells and the Felix Candela shells,
Yes.
they built in a lip to reinforce the arches. They actually designed.
Of course.
And you found
But
one that designed itself.
exactly.
Another round of applause.
But you know, even Felix Candela was a good friend of mine.
Yeah.
I met him in Mexico. I met him in many parts of the world. And Mario Salvadori, who was the man who invited me at Columbia University, he was a great mathematician, and he is a part of the Manhattan Project for the atomic bomb with Fermi. So he was actually. He could not believe that a mathematician, an engineer, a professor, a civil engineer. He said, it is impossible that you do this. And indeed, the professor come to see it. And he came in Italy to see it. And then he invited me to Columbia University. There is a photograph to actually design and build in the campus for the first time in history of the School of Engineering of Columbia University. This is it. All the press was present. The day after, the New York Times, 3 pictures like this, in the first page of the second section of the newspaper. It was something that people, even professional, would not believe, particularly considering that you can lift up 300 tons of wet concrete and steel with the pressure that you make puffing a cigarette, as Nick was saying. It's ridiculous. When we calculate the cost of those buildings, we said energy 0. You cannot go better than that.
That's why we encourage everyone to use the workshop. It's shop for Christmas, I'm sorry.
Yes.
Don't get me wrong, I love this idea. I know it's working, but in your perfect world, let's say this is a very giant thing and everyone is using it. So basically, in your perfect world, is the surface of the world a bubble wrap? Is everything circular? Isn't it losing a lot of space and isn't it very boring?
Well, it is boring now to make it every square, but I think it's time to change a little bit. Yes.
I mean, like, basically, in your perfect world, everything would be this shape.
No, this isn't so much the
Is
denomination.
it changeable?
That's why we're here, in fact, to address what you're saying. This is a solution. You know, it's a new way of thinking about construction. And our perfect world is where, you know, Binishell, I did a calculation, and if Binishell captured 0.5% of the US housing market, okay, it would be the same as taking 90 million cars off the road in terms environmentally per year. Plus you'd be housing people in safer buildings. That's the perfect world. A percentage of construction, you know, being built with this system, and then another 0.5 with your system, and all the other smart people will have one too. We have to build differently. That's the point.
Can I add something about that? I mean, we were seeing a stats that you showed about 50% energy, 40% CO2 emission. have CO2 emission 50% of
40.
the actual status quo of our city, of our world, how we do reduce that with your system, because we will never be able to change that 50% of CO2 emission given the actual architecture in Western City, what we have as existing building. They got there to stay. And if you go in to a planner today, you go in with that geodesic shape or double curvature and try to figure out that with this intervention I will emit less in CO2 in this city, specifically London or in Italy or in New York, it's going to be a very big fight and very likely not to be granted planning permission
Well,
because of you know, whatever we
this-
want to do.
this
Perhaps
building,
this is a very
this building here,
selective
I understand your point.
market. It's
Yes.
a market which is reclusive. Well, I wouldn't say reclusive. Perhaps it's a very niche market for away from the city, where there is already a precedent of reality of the city, which has got its own language of architectural and character
yeah.
that we have
The-
to cope with.
The
And therefore
situation,
going out.
the
perhaps it's
situation
necessary.
today is that, sorry, the situation today, you cut me off, so it's only fair.
Okay, so.
The situation
Italian,
today
you know, Italian
is
style.
that the need for housing around the world is in the order of 50 million units in the next year and a half, okay? And that's simply in 3 countries. So it's not like we're going to remain at the status quo at 50% if we just keep going the way we're going. We're going to get up to 60 and 75% of a bigger polluting pool. So it's important to think about how we can build bigger, better from an environmental standpoint, just to stay at the status quo. That's the first point. Secondly, yes, but hang on just a sec. This, this building here is being built in Malibu. Some of you may know that Malibu is considered the most difficult place to get permits in the world because it has very stringent environmental issues as well as the California codes, as well as the Coastal Commission codes, and the seismic issues that you get in California in general. And it's flown through the permitting process faster than anything ever before. So if you understand codes in the same way that we challenge you to understand materials, you can come up with realistic solutions. And that's really the trick if you want to, you know,
Sorry, when you say codes, what
construction codes.
regulations?
Codes.
Oh, wait, Italian. This could go on all night.
I mean-
Just let Victoria say something.
Can I ask the same question of this proposal that I asked your father about the Michelangelo and Antonioni house? How much of the technology involved in that proposition is shell technology?
So essentially all, so, you know, this,
It looks to me like there's only a tiny bit.
All the stuff that deals with gravity, Victoria, is shell.
the entire cover is,
Is the ground shell?
no, this is not. But the entire cover here,
I want to answer, I think the perfect
That's a
world
green
question
roof.
is very important to address. What, you know, a soap bubble, a perfect world for a soap bubble is never going to be a cube or anything orthogonal. Nature doesn't tend in that direction.
Have you seen a chicken egg?
You know,
Square? Cube?
engineers look at nature because it's astonishingly efficient. And the soap bubbles form, they're not going to naturally, a soap bubble's perfect world would never be orthogonal, never be a cube. So as an engineer, which is kind of what we're talking about here, efficient engineering, it's never going to happen. We're never going to get that, ever.
I don't pretend that we are going to cover the world with Binishells. I only suggest you to think in a different way, because we are wrong in proceeding in the way we are proceeding now. I hope that this doesn't help you to build Binishells honestly. I want you to think that there are different ways. For example, one example, to use air pressure as energy. You know, we don't have the time. But I was requested by the same Japanese group that wanted me to help them to build this incredible pyramid to design lunar bases using compressed air as energy on the moon. So I was shocked about this question. I mean, I said, the man more ignorant in the world on astrophysics is me. Why you asking me to say, I know, I was there when you built Expo 17 and was presented at the International Federation Conference at Washington, D.C., and was applauded as one of the most innovative ways to produce those lunar bases. So what I'm trying to say, that I don't want to follow exactly what I'm doing, to be critical on what I'm doing, but don't be critical to return back to history. Try to do something new. And the power of your brain, I'm sure, will discover something different and something new. This is what I'm trying to say. You have a question?
Yeah, I had a question about the Americans. We mentioned the Americans before, and one of their problems on why they use so much energy is because they build like that. They build so spread their suburbs so widely, and they use so much energy for commuting and traveling. And is like building like that exactly is not the answer, is it?
No, it's not. It's one change, a tentative to change things. And I have, as I said before, we are working on a multi-story building built by air.
Yeah.
This is what was the answer. Yes?
How are you seeing your technology being adapted by the emerging market, namely China and stuff like that?
Can you answer to the question, Nick?
This gets back to the idea that, you know, we don't have all these solutions. But what we've seen is in some markets, big players are seeing interest in our technology, which is showing some market appeal. China, you know, we're talking about high density. We can really only do low and mid density today, but there's new systems coming. What we do know is that low-cost housing and high density have typically not gone together very well. So it's not probably going to be, and who knows really what the answer is, but history teaches us that if it's low-cost housing, it may not be high density. But yeah, the Asian market is huge, and the need is tremendous. And this is a faster, cheaper, faster, more affordable, greener, and stronger way of building. One solution. And again, don't know if it's the right one for China, but there's a real opportunity there for all of us.
Yes?
How do you actually, as a designer, as an architect, or let's say the person responsible for the spatial layer and the actual shape, do you have guys like a design guide? I mean, how do you go with the curves and what kind of circles are you, let's say, what are the kind of joints? What are the volumes that can be, let's say, merged or, let's say, added? Like,
Yeah, fascinating question. And there's no real answer to that. But our approach is this. We see ourselves today as a technology company working within construction. Strangely, that's a novel idea. So we've developed some prepackaged systems that address what we see as the biggest areas of need within the construction market. Housing and education, low-cost housing, and disaster relief housing, as well as infrastructure projects. Now, as part of doing infrastructure projects, we're doing high-end custom homes for famous people, because guess what? That's how generally the market works. It's, I want to be like him, and if it's good for him, it will work for me, and that's part of marketing. So we're doing these projects as well, but this is what we see.
One second, before you, can you go back on that picture? Because I think this is the best scheme, in my opinion, so far that I've enjoyed in this presentation. How much can you cut off from that skin? the roof scale? How much can you get rid of it? Because
May-
obviously
may
we're
I
talking about
answer?
energy and lights. I just want to understand how much can we modulate and manipulate with that surface?
Okay, depend of the intensity of steel that you have in the thin shell structure. You may have seen in some of my domes that I cut large portion of dome, even without putting a reinforced ring beam around, because the steel intensity is so dense that it's like a ferro cement of nervy type of thing. So in this, in the case that was before, I think that what I did in Australia when I was cutting large portion of the dome, I was building arch beam inside the structure, and I connected the steel and the concrete to the shell itself. Of course, this is more expensive.
So do you have some sort of scale parameter? Somebody say,
yes.
How much can I remove from the shell?
Exactly. And so you have to more or less know in advance.
We're talking about 2 inches and a half?
3
inches and a half,
yeah.
which makes up the shell.
Well, even in,
Should
do
be
you remember how much it is?
To your picture.
Yeah. Let's pay my.
This
Before
is
we get
actually.
into a crit, ladies and gentlemen, I think we should say thank you very much. We'll move it on to a conversation later, but we say thank you so much for coming.
Okay.
Thanks a lot.
Thank you. Now the ball is in your court, so play it.